Well, happy Cinco de Mayo. I'm Kevin Fincher, the CEO and the president of the Austin Regional Manufacturers Association. And this is the Manufacturing Austin podcast, where we bring you great, innovative things that are happening in the Austin, Central Texas manufacturing area. And we're really excited today to bring you straight from the floor of Aalo Atomics. And we're going to have an interesting discussion, I think, today on all things not only nuclear, but on how to build nuclear, because this is, after all, manufacturing podcast. So I want to thank our longtime sponsor, Texas Mutual, for once again sponsoring our Thought Series and being a friend of manufacturing and helping support manufacturing. So thank you again, Texas Mutual. And we're excited, again, to be here in the factory floor. So I want to thank our friends at Mylan Media, who are behind the cameras today producing the podcast. So thank you. It's a nice rainy day. We didn't expect that when we walked in, but I think we've dried off pretty well, and we're ready to go. So with that, let me introduce our special guest of the day here. So Yasir Arafat. Should we just address that right there? Yasir Arafat, you know?
Yeah, it's a famous name. Let's put it that way. So.
But you're not that Yasir Arafat.
No, far from it.
You're nuclear Yasir Arafat.
I'm nuclear Yasser Arafat. That's
all
right.
right.
That's right.
Making a new reputation. So, Yasir Arafat, introduce yourself.
Sure. Well, first, Kevin, thank you so much for having me on this podcast today. For the audience, I'm Yasir Arafat. I'm the co-founder and CTO at Aalo Atomics. So we are a technology company, and so all things technical I oversee, including our design and development of the product. I also oversee the manufacturing and our capabilities of building these reactors in-house, as well as our fuel supply chain and our regulatory work. So, yeah, that's my role.
That's a lot of things in that role, but we're going to dive into that today and dig a little bit deeper. So I always like to ask a personal question and ask about hobbies. I know when we were in the lobby, we talked a little bit about one of your really cool hobbies, but talk about that a little bit, what you like to do to relax and decompress.
You know, since I was 3 years old, I like to build things, and that came in different form factors. I used to do a lot of art growing up. Pastel, watercolor, Japanese sumi ink, acrylic, charcoal, did everything you can think about, and also got into a lot of mixed media. And then right when I was in around elementary school, I also like to do a lot of fireworks and play with magnets. I was sort of a pyromaniac for a little bit, and then got into a lot of woodwork as well. Built
You
a lot
didn't get
of
into a lot of
furnitures.
trouble with the fireworks?
No, not that I could. I want to mention here necessarily, but yeah, it was a lot of fun.
All right, well,
But
good.
kind of to answer your question, outside of building nuclear reactors and factories, I'm into art a lot. In fact, if you come visit our Austin headquarters, at the entrance you'll notice a kind of a life moss art piece, and that has a little bit of a background to it as well, which, by the way, I built in a day and a half.
Yeah.
And the story there is it's an aerial view of nature that has portion of like a forest view, some hills, some mountains, some lakes, and the idea is, if you want to have humanity kind of grow as a species, we need plenty of amount of energy for us to thrive. And if you use extensive amount of fossil fuel, we're going to affect the environment. And if you use a lot of solar panels, for example, which are considered renewable, but you do a lot of deforestation to put the solar panels down. But the idea of that artwork was, it looks like it's completely nature from the aerial view, because if you use nuclear energy, which is very, very compact, you don't really disturb the environment too much. And that you can actually have both. You can have humanity prosper with abundant energy, as well as not, disturb the natural environment that we live in.
Yeah.
So, yeah.
No, and it's a great piece of work. It's very relaxing to look at it, and that's one of the things I love about Aalo, is just kind of the environmental mission of bringing clean energy resources to it. So, the company's values in mission, right? Talk to a little bit about that and what you guys are trying to achieve.
Yeah, and our whole entire vision is we want humanity to prosper, and we want that prosperity to be untethered from the environmental impacts that we can have. And again, every energy source has some sort of environmental footprint, and we believe nuclear is this underdog technology that can provide that abundance without really, affecting the environment that we live in. And our mission, the way we think about how we can make this vision come to life, is to make nuclear energy accessible and affordable by many. So right now, if you look at nuclear energy, it's like 20% of our electricity in this country comes from nuclear, and most of those plants have been built, from 50s to mid 70s, but we haven't built new nuclear plants for quite some time, apart from Plant Vogtle Unit 3 and 4. And if you look into those older plants, they work just fine. They're plenty safe. We get reliable electricity out of it. But if you want a new nuclear power plant, it takes a while. It takes more than a decade to build these days. And so, we're trying to make a difference there.
More than a decade and billions in cost overruns usually by the time it's done.
And we'll get into that more in details.
Yeah. So that's kind of talk about nuclear in general, because I grew up in the 3 Mile Island era, and that really caused a lot of people to pull back from nuclear and look at it as a dangerous source. Chernobyl. I mean, you can go through the list over the years. We're talking about something different now, right, as we move forward. It's not the big, huge plants anymore in the cooling. It's going to be about what we'll call the small modular reactors, and we'll differentiate against the categories on that. Why the renaissance in nuclear right now? Has the technology changed that much that it's suddenly come back and now it's being acceptable to be in nuclear again?
Yeah, I think there's a few factors, right? So if you look into, there was a lot of, as nuclear was ramping up, there was more and more regulations coming into the scene. And I think the 3 Mile Island accident was the nail in the coffin for nuclear energy's growth in this country. But if there's a lot of hysteria and people were freaked out about the whole 3 Mile Island accident, which, there was a core meltdown that happened. But if you look at the actual data, there were no fatalities because of 3 Mile Island, right? Nobody died out of it, but it's just that people got quite freaked out by it. And so, that is a consequence. We want to make sure that people don't feel that way. But the real data, you'll see, it wasn't, the way we operate nuclear power plants in the West, this is probably one of the safest energy industry you can think of, as far as how many fatalities that we have had versus how many kilowatt hours of energy that we produce. But you're correct. I mean, the plants that are currently operational right now, they're fantastic plants. We've been running them for decades without having any major problems with proper maintenance, and we operate them very well, and they operate at very, very high capacity factor. But the challenge that we face right now is, over time, these power plants, because they're complex, there's a lot of systems around the nuclear reactor itself. For you to really make it economical, you want to take advantage of economies of scale. So they used to be smaller, and they grew in size as time moved on. So now, these power plants are, over a gigawatts, right? And at some point in the curve, when you try to build such a large, complex, these are one of the largest mega structure that humanity can build. It can take more than a decade, right? And if you build it, again, just like everything else, if you build it over and over again, that number comes down. But the challenge that we have seen with Plant Vogtle, Unit 3 and 4, the original cost estimate was $14 billion. And ultimately, when everything was said and done, it was close to 30. So there was significant cost overrun. The time that was originally planned nearly doubled. It took us like 15 years, which is non-trivial. And so if you look at, a lot of the utility companies in the United States, they have about 8 utility companies have licenses to build AP1000, but we're not building them because of this big elephant in the room is schedule and cost overrun. So I think as a nation, we're willing to figure out a proper mechanism how to make that happen. But when we were starting Aalo, we thought, is there a different model we can think about? Instead of taking a decade to build a gigawatt, is there a way we can speed things up? And how do we do things differently? And so there's this whole new, I shouldn't say new, the idea that we thought about is, let's go, instead of building 1 gigawatt giant scale plant on site by traditional construction, why don't we shrink the reactor down into smaller reactors and make them in factory setting, and make them in tens or hundreds of these, just like we make cars or jet engines.
It's the Henry Ford factory line.
It's the Henry Ford, assembly line for nuclear reactors. Now, this idea is not new. I must tell you, since the 50s to now, there was a lot of different, thoughts about, hey, what if we could build nuclear reactors in factories? But if you look around, there are no factories that build nuclear reactors. So, we took a different turn in history on using economies of scale rather than economies of multiples. But if you look at any other high-tech, complex engineering industries, whether it's jet engine, cars, planes, even data centers, for example. We don't build one giant computer. We build smaller computers and we stack them up in a rack and a row and build data centers out of many smaller computers put together, GPUs put together. So I think a lot of the other industries have successfully leaned more on economies of multiples than economies of scale. So that's what Aalo is trying to do. We are trying to come up with the ideal technology that can have a pretty high power density, meaning from a given volume, we can extract a lot of power out of the machine, but also that it's designed to be built in a factory. Not every nuclear reactors are optimal for that, right? Most nuclear power plants, you've got a significant amount of on-site civil construction project activities on site to build the building and all the equipment's brought in, and a lot of these are equipment and modules you build elsewhere. So what we are trying to do is not only we build the reactors in factories, but we also want to build the overall civil structural plant in factories as well, so that when we go on site, the tasks or activities that's remaining is very small.
Yeah.
So we can pull this off in a matter of months, not years.
That's great. So just to clarify, I struggle with this all the time, right? We throw around terms like gigawatt and megawatt. Like, what does that mean? What's a gigawatt? We talk about, Texas is growing, energy demand is growing as data centers come online, as industrial comes online, and ERCOT is out there talking about a 5-year projection where I think it's like 45 megawatts. And what's a megawatt versus a gigawatt? And I don't know, what did I say? That 45 megawatt ERCOT? It's actually gigawatt, right? It's much bigger than the megawatt.
Yeah, so let me break it down for the audience who are not familiar with these terms. So 1 gigawatt equals to 1,000 megawatt. So just to get a frame of reference, when we talk about 10 megawatt, for example, that's equivalent to about 10,000 homes power, right? So when you talk about a gigawatt, it's 1 million homes, roughly speaking. So, it's kind of a small city equivalent.
Okay, that's very good. And we'll get into this, I think, talking about behind the meter and kind of where you guys can go and this deployment. It'll be interesting, talk about that as a source. So This is the Manufacturing Austin podcast. We are here in Austin, Texas. Governor Abbott has made it a priority that Texas will lead the way on nuclear, and we're going to embrace nuclear. We've got so many different projects that are happening. What's the importance of being in Texas and maybe Austin as well? What drew you guys here?
So that's a very interesting question because, neither myself or my other co-founder are from Austin. And so
Matt, your co-founder.
Yeah, Matt is the other co-founder of Aalo Atomics. He's the CEO, and I'm the CTO. Matt is from Ontario, Canada, and at the time I was living in Idaho because I was working at Idaho National Laboratory, and then we actually made a list of criteria on where we should set up Aalo, and what we found out was Austin ranked pretty high, and the criteria was we need an environment where the state is a champion in energy. And if you look at Texas, they are the champions in deploying almost every kind of energy, not just fossil fuels or oil and gas, but also if you think about the largest wind deployment is in Texas. One of the largest solar deployments are in Texas. And I think they're going next to batteries, right? They want to be number one in batteries, and I think organically, it makes sense for nuclear to also become a prominent part of this state's energy mix, which we already have nuclear power plants here. But if you're looking for a state that wants to be a leader in energy, it's the state of Texas. So that's number one. Number two, we also want an environment where you have a pretty decent workforce that can support manufacturing. We've got from the oil and gas sector as well as a lot of space. Tesla and other deep tech companies have also moved to Austin. So there's a rich culture of manufacturing talent around this area, which is kind of very unique. And three, we also like the fact that Texas is a proponent of nuclear energy. Right, just like any other energy form, they're not opposed to nuclear energy. They actually are very supportive of it. So we really like that a lot, and we wanted a place that has relatively decent cost of living, which Austin is, and then relatively majority of the time we have good weather.
Yeah,
other than the summertime, right?
We got some rain coming in right now, so maybe you can hear that. But
yeah, 9 out of 12 months we've got decent weather. Yeah. Summer gets unbearably hot, but that's doable.
Yeah.
So those were the criteria. I mean, primarily it's because good support for energy, good support for nuclear. We can get a lot of manufacturing talent here in this area, leveraging a lot of the oil and gas sector specifically. So that really helps us a lot.
Well, I love the fact that you talked about workforce, which is one of ARMA's pillars, and we spent a lot of time in developing workforce. We, clearly that's been in semiconductor and automotive, but we're seeing aerospace in DoD. But now we get to talk about nuclear because I think that's cool as well that we have that. So glad that you brought that up, and that was one of your drivers in wanting to be here. We do think Austin's still weird. We're trying to keep it weird, so
we like it that way.
We like it that way. Really excited to have you guys here. So that's all great. Now let's talk about the timeline, right? Because when I run around, I talk to different people, energy companies or other folks. They keep talking about maybe the mid 2030s that this technology will be commercially viable. I think you guys have a little bit different timeline, which I think I'm pretty excited about. Talk about your timeline and where you guys think you're going to be.
Yeah, the way we see ourselves at Aalo is we are a speed and economics company, right? So obviously we want to make sure we design a product that is economically very compelling, we can talk about that. But the other part of it is speed. And so we like to think ourselves as, we don't take any shortcuts, but, we like to do things very fast. And so if you kind of look at all the things we were able to achieve the last 2 years when we put the team together, there's a lot of our peers in the industry who have taken like 5 or 6 times longer to achieve the same things. And so we try to move a little faster. And our timeline right now is, we want to build our first nuclear reactor, and literally we will start construction 12 months from now. So April of 2026, we want to build the first experimental reactor. And the reason we are doing an experimental reactor is because it's a new and a novel technology. We want to make sure that it works as we have designed it, and we can operate it well if there's any changes we want to make. So we're not jumping directly into a commercial project right away.
Is this the Idaho project that we're talking about? Okay.
So we call this plant the Aalo X, like Aalo Experimental Reactor.
Okay.
And we're actually building, this is a 10 megawatt electric or 30 megawatt thermal, kind of a single reactor, steam generator, and a small turbine. And we want to demonstrate that at the Idaho National Laboratory. And the reason we selected INL to build this reactor is because, obviously I worked there, I know all the infrastructure and all the people in that space. But also, if we build a test reactor, which is an experimental mission to it, and it's in a DOE site, Department of Energy site, it does not have to be licensed the same way as commercial systems. Rather, the Department of Energy can authorize the reactor rather than the U.S. Nuclear Regulatory Commission. Right. Now, why DOE? Because we have gone through this process previously with the MARVEL program that I started at the Idaho National Laboratory. So we understand the process very well, and the process itself is very flexible and agile, and we can move through the learnings very quickly. And the DOE Idaho Operations Office is very supportive of us doing this, taking the learning from a fully funded Department of Energy program, which was the MARVEL reactor, and taking all those learnings into the commercial space. And we're bringing in, private investment to build the Aalo X. So I think it's going to essentially take all of the R&D that MARVEL did, and before MARVEL, it was EBR-2, the SRE reactor, HALEM, all the various sodium-cooled reactor programs we have run in this country and beyond. We're taking those learnings. We took those learnings and put it into MARVEL, and more. Now we're taking the learnings from MARVEL and taking it to the commercial space. I think this is a good success story for the Department of Energy. And they're very supportive of us, trying to demonstrate our first reactor there. And so we have gone through many of the various steps that we need to build this reactor, and our current timeline is April 1st, April Fool's Day. On 2026, we will hit the ground for groundbreaking.
Well, let's not fool anybody on that. Let's make it real.
It's going to be a real thing. Now, that's our first experimental, or first nuclear reactor. Now, learning from that is ultimately going to go in our first commercial product. And we're not trying to do them in series, rather somewhat in parallel, so that when we finish the design on the experimental reactor, the team can shift to finishing design on the commercial product. When we finish construction on the experimental, they can quickly move to the construction of the commercial product. So we staggered these back to back, and so based on this, our timeline is we want to start construction of the commercial product by 27, complete and install everything by 28, and then go critical by 2029. So that's kind of like our timeline right now for commercialization.
All right, so you heard it here first. By the end of this decade, we're going to be commercially producing, we'll call it small modular reactors, or in your case, you call them XMRs.
Yeah.
Extra
modular reactors.
Extra modular reactors. So I want to talk about the three tenets of Aalo in a minute, but let's talk about the underlying nuclear technology that you guys have, because it's different, right? It varies totally. A little bit from what we historically have been used to with coolant and water coolant and all that other stuff. So let's try not to lose everybody on the technical side, sure. But let's differentiate your technology from what you would typically see others using?
Yeah. So for those in the audience who don't understand how nuclear reactors work, it's actually basically generating heat. No different than a coal plant. In a coal plant, you burn coal, get heat, and you use that heat to make steam, and we pass that steam through a turbine, and the turbine rotates and makes electricity. In a nuclear power plant, currently, we basically have a reactor vessel, and we have nuclear fuel, which looks like metallic rods, and we stack them in a bundle. That's what gets heated up because of nuclear reaction, because of splitting atoms of uranium inside the fuel, and that generates immense amount of heat, and we remove that heat using water as a coolant. Now, for you to make steam and high temperature steam, you have to make sure that you can extract that heat safely without boiling the water away. So what we do in current reactors, we make the reactor vessel a pressurized system. So normally what happens in your kitchen, when you try to heat up water at 100 degrees Celsius, it will tend to boil away. But if you have a pressure cooker, that boiling point raises up, right? So essentially a pressurized water reactor, as the name suggests, is you pressurize the water to operate above 300 degrees Celsius to make steam. Essentially, there's a primary side and a secondary side, and you ultimately generate steam that turns a turbine to make power. Now the challenge with a pressurized system, particularly that uses water, is you need a lot of different supporting systems around it to maintain the pressure. Water is a universal solvent, so you have a lot of chemistry management and control. And to make these systems pressurized, all your steel structures like pipes or vessels have to be very thick-walled, and that increases up your cost. So what we have done in our reactor is, one of the first things that we said was, let's not have a pressurized system. Now, if you look at a lot of the advanced reactor, which operate even higher temperature, they're using a gas to operate for their coolant. And that also makes the system pressurized. And you have to also get forged vessels. We are a non-pressurized reactor vessel. And the way we achieve that is, instead of using water or a gas, we use a liquid metal as our fluid, as our coolant, to take the heat away from the nuclear core. And specifically, we use liquid pure sodium. Now, sodium is a little bit of a challenging fluid because it tends to react with water or concrete, air. It's a reactive material. But as long as it's confined in structural steel, it's the most compatible fluid with structural steel than even water and steel. So it can operate very long time, and by maintaining pretty decent chemistry. All you need is basically a small, what is called a cold trap to remove the oxygen from the system. And you can maintain very high purity operation between austenitic stainless steel and liquid sodium. And so this is not new, by the way. In fact, in this country, we've built many sodium reactors in the past, and one of the latest experience I can point to is a reactor called EBR-2 that was built at Idaho National Lab. It worked for 30 years just fine. And what happened was, when you have markings inside the reactor vessel, during fabrication, fabricators used to have markings inside the vessel. They operated 30 years and then waited another 20 years or so for decommissioning. And then when we emptied out the sodium, they still saw those markings on the wall. That's how good the chemistry can be between sodium and steel. So we're using that coolant that allows us not to have a pressurized system, so our walls are thinner, and we can actually move away from forging to getting standard metallic plates, roll them up and weld them and make reactor vessels out of standard manufacturing methods using plates and welding rather than complex forging, for example. And similar to the reactor vessel, We have looked at every single other components like pumps, heat exchangers, our grid support structures. All of these components are designed so that you can optimally use standard equipment, standard manufacturing processes to make and assemble these instead of requiring bespoke, complex, jigs or custom machines to build these reactors. The other property I want to highlight on sodium is it has very high thermal conductivity, meaning you don't have cold or hot spots. It tries to keep, when you heat it up, the whole bulk fluid tries to stay at roughly the same temperature. This is super useful because all you're trying to do in a nuclear reactor is when you generate heat, you want to be able to remove that heat effectively without having hot spots where things can bend or bow or melt. So we want to avoid, those kind of phenomenon. So sodium, its thermal conductivity is very high, and so it keeps most of the content of the reactor rather isothermal. And that allows us also to remove what is called decay heat very effectively. So those of us who are not familiar with nuclear reactors, unlike a car, right, where you have an engine, and as long as you provide fuel, oxygen, and a spark, it will combust. And the moment you shut off the car, it's dead. There's no more reaction. In a nuclear reactor, you have full power operation, but when you turn off the reactor down, it does not go cold right away. It produces initially 7% power and then decays it down to about 1% within a couple of days. And so it still produces heat, very small amount, but it still produces heat. If you don't get rid of that heat, things can get heated up and bad things can happen. So you want to make sure that you can safely remove that heat effectively. In current reactors, we have large pools of water or diesel generators as backup to ensure cooling after a reactor shuts down. But what we are trying to achieve with our reactors is that when you turn off the reactor, ambient air, surrounding air, can basically come in, and the air around the vessel can get heated up. It will rise by natural convection and bring in cold air in and hot air out. Very similar to what we see in chimneys, right? So it uses physics to naturally cool it down once the thing is turned off. And that is also very effective. When you have a conductive coolant, it moves all the heat from the center to the side of the vessel, and you can remove the heat effectively. So we don't try to use a lot of man-made systems or rely on the operator for safety. We try to use physics as much as possible to ensure safety of this machine. Now, without taking a look at it, it's very hard to visualize what such a machine can look like. So I'm glad you're here at our factory. We can actually show you one if you're interested.
You know what? This might be a good moment to actually show it rather than trying to describe it. Right?
All right, let's do it.
Should we do this?
Let's do it.
So for those people who might be watching, we're going to do a grand reveal right now so that you can actually see what this technology looks like. If you're listening, go back and take this moment and watch this because you're going to see what this looks like. So should we do it? Let's do the reveal.
Let's do the reveal.
All right.
Okay. It's kind of a non-conventional reveal in a podcast, isn't it?
It is a little bit. So again, for those who happen to be watching, this is what it looks like. This is what the Aalo technology is, and you can kind of see the scope, the size, and what one of these would look like. So before we kind of jump into this, I want to go back to another, I think, essential question as we start to look at the energy supply source. You talked about sodium. I didn't realize that sodium could be a liquid metal. I just think about my high blood pressure when I put sodium on there. But the plutonium that goes into this, there's different grades on that, right? Is that ample energy source here in the U.S., or are we dependent on foreign countries for that?
Yeah, so you're talking about what fuels these reactors and where does the material come from. So our fuel form, and this kind of very important point, is the same exact fuel form that we use in conventional current nuclear power plants. It's a material called uranium dioxide. Um, why is that important? Because if you look into current reactors, they operate at a certain temperature that's about a little bit above 300 degrees Celsius. Now, for us to achieve a higher temperature, we need to move away to different types of reactors called advanced reactors. And advanced reactors have different kind of missions. Some of them are geared towards, getting more juice out of the fuel, or burning nuclear waste, or achieving higher temperature. And you can, there's three or four different types of main categories there. The interesting thing about those advanced reactors, they also use exotic fuel. Like, there's a fuel form called TRISO, which are basically like uranium kind of trapped in this multi-layers of a bead, and you take these, and these beads are the size of the tip of a ball pen, and you collect them together and you make the fuel form. There's benefits of that fuel form called TRISO, in that each individual kernel is trapped in its own little layer of protection. So some argue that even in the worst case scenario, it's not it's a safe fuel. It's a robust fuel form, which is a plus. But the downside of that fuel is that when you build a reactor out of it, the power density, which means from a given volume, how much energy you can extract out of it, is very low. Like, to give you an example, from a cubic meter volume, the most you can extract out of this fuel form is 5 to 6 megawatt. Whereas in conventional reactors, current reactors, it's more than 100 megawatt from that same volume. So power density matters because, you're paying for stuff at the end of the day, per how much energy you extract out of it. So when we Aalo started looking into technologies, we wanted to make sure we use a fuel form that has high power density, and so the uranium dioxide fuel, fit that profile. The other advantage of this is because this is an existing fuel form, there are existing companies that makes thousands of kilograms, close to 1 million kilograms every year. We can rely on that supply chain, which is very mature, to get our fuel, not for our just first reactor or second reactor. If you want to build hundreds of these, we don't have a scarcity in where this fuel is coming from. So that's number one. It's very important. So we're not just thinking about, onesie twosies. We're thinking about how to mass manufacture and deploy at scale. And if you use anything else besides UO2, it will take you multiple years and many hundreds of millions of dollars in investment to come up with those new fuel supply chain. So that's number one. The chemical form is important. The second is something called fuel enrichment. So uranium comes in two different types of isotopes. And one is uranium-235. In nature, it's a very small fraction compared to uranium-238, which is larger fraction. So, the actual fuel is the U-235. So we need to enrich that to increase the isotopic ratio of U-235. And current reactors are about 5%. And we have a commercial supply chain for that. However, advanced reactors, they try to go to a higher enrichment, which is called HALEU, high assay, low enriched uranium. That's like, between 10 to 20% roughly. The challenge with HALEU is it's also exotic. Back in the days when, about 10 years or so ago, when advanced reactor companies wanted to build their reactors, they thought HALEU was a good idea until Russia invaded Ukraine, and a lot of the HALEU was going to come from Russia. That was our fuel source, right? And that got cut off. Now we don't like to do business with Russia, And so now the United States government are trying to put hundreds of millions of dollars to stand up our own HALO capability, but that's going to take a couple of years before we get there. So what we are trying to do, we saw that as a challenge because we don't want to wait around, 5 to 8 or 10 years before we can get both HALO and other fuel forms at a reasonable scale and cost that we can use them in our reactors. We wanted to leverage existing fuel supply chain as much as possible. So we are not HALO, we are LEU plus, we are at 8% enrichment, which industry has licensed to ramp up to that level and has existing facilities that can make this fuel form. So I think it's super important to point that out because we're not using any exotic fuel form or high enrichment that we cannot obtain today. And so we can scale, as long as we can build these reactors and multiples of them in a factory, we should have ample amount of fuel supply in this country. Now, to your question, where does this uranium come from? So 99% or more of uranium that we use in current reactors are actually imported. They're mined in Kazakhstan or some other countries where we basically take those material, bring in the country, and then we essentially convert them into the chemistry that we need to provide our fuel form. And so I think, with the whole changing environment that we see with the new administration, with tariffs and others, we don't see them affecting uranium too profoundly just yet, but that could change any day. But that's something that we're keeping a close eye on. But nonetheless, I think we've got enough margin in our cost estimates to absorb any of that uncertainties.
We got this prototype reactor sitting behind us here. So let's talk about Aalo, and let's talk about manufacturing, since this is a manufacturing podcast, because that's ultimately where we want to get to. You've got effectively 3 legs, is what I call it, in Aalo, right? There is the reactor itself. There is then the pod. Let's talk about the Aalo Pods in a minute, where you take these reactors and you combine them, and you can then generate the power and put those wherever you need that power source to be. But really, again, the exciting piece on this is the actual mass manufacturing. What we'll call, we have a gigafactory here, but you're a gigapower factory is where you guys are going, right? That's the ultimate goal, is to be able to produce a gigawatt of XMRs on an annual basis, correct?
Yep.
Okay, so let's start real quickly again with our reactor, because we've been talking about all the technology that goes into this. This is 10 megawatts that's sitting behind us. This is what this will produce?
Yeah, so if you think about the thermal energy, this will produce 30 megawatt thermal.
30, okay.
And then from there, if you convert to electricity, it can generate approximately 10 megawatt electric.
Okay.
Right? So it's roughly about 1/3, when you do the conversion from heat to power.
And then you take these and you string these together. So you can put 5 of them together, and you can get 50 megawatt of electricity.
So, a lot of the nuclear industry, the way they define their product is by their reactors, right? I've got a 100 megawatt reactor or 1,000 megawatt reactor, and that, rightfully so, right? Each unit is very complex on its own, and so the heart and soul of the power plant is the reactor itself. The way we define our product is not the reactor that you see behind us, right? That is just a component in the product. Just like in your car, if you have a V6 engine, you've got 6 cylinders pumping, right? But the engine is really, the power generating system, but your car is your product, right? Not the engine. You don't go out to the car dealer and say, give me a V6 engine. You say, give me a car, right? That's what I want to buy. That's the product the customers use. So for us, the reactor is not the product. The product is the power plant. So when we wanted to focus on a particular product, we wanted to not create a generalized product that applies to everybody and not be good at anything. We really honed down on a specific market. And the market that we honed down are actually data centers that once power in, around 50 megawatt unit blocks, right? Back in the days, data centers used to be like 10, 20, 30 megawatts. Now they are like 50 or 100 megawatt unit blocks. And you can see like data centers getting multiplied to get a gigawatt worth of IT load or more, right? So our individual product, our unit power source is what we call the Aalo Pod. So the pod would comprise of 5 of these reactors connected in a row, and they will all provide steam to a single turbine that is going to generate 50 megawatt electric. So 5 reactors, single turbine, that's our product. That's called the Aalo Pod. And it's purpose-built for providing on-site power to data centers.
And it's designed to really kind of be very aesthetically pleasing, right? It's not these ugly towers that are sitting around in somebody's backyard, right?
Yeah, I think that's an important aspect which a lot of the folks overlook is, right now if you look at conventional nuclear power plants, they look kind of dystopian scary, right? And if we want nuclear systems that are extremely safe and can be, pretty much co-located in people's backyards, we want them to not be an eyesore that blends beautifully in the background. So we are also putting a lot of emphasis on the architectural design and beauty of these Aalo Pods, which looks like, some people say they look like barn inspired, but it's like, we call it chalet inspired.
Chalet, okay.
Right? We want these structures to fit in nicely, whether it's in the back of a data center or powering a community or an industrial facility. We want them to look like, friendly and welcoming without exceeding cost or making it extremely like futuristic looking, right? So that's very important to us. And yeah.
Well, hopefully visually here we can insert maybe a couple of the schematics of that so people can visually see what it is. I was pleasantly surprised when you revealed that and showed what the pod actually looks like, because it was very appealing. I thought of it as as a European kind of chalet thing, and you wouldn't realize, that you're looking at nuclear power plant in there. So that's like leg 2, but at the end of the day, you still got to make a whole bunch of these, right?
That's right.
So
that's right.
The factory.
Let's talk about that. Okay, before we talk about the factory, I do want to talk a little bit about the XMR leg, and that can lead to the factory portion nicely. So if you look into existing nuclear, we call them they're about a gigawatt scale, so we call them conventional plants. And back in the days, about a decade or 2 ago, industry thought these plants were too big, let's try to make them a little smaller, easier to finance, but same technology. So they're essentially 1/3 the size of gigawatt scale plant, like 300 megawatt or so. These are called small modular reactors. They're small compared to larger reactors, and the reactor may be modular, but the plant is not. It's still a large civil construction project. So what you're doing is you're shrinking the larger scale power plant into something smaller, but some of these designs need as much concrete or as much steel as the large plant, except you produce 1/3 the amount of power. So the economic story is not as compelling, or the timeline story is not as compelling. These are called small modular reactors. Now, on the other end of the spectrum, you'll find like really small, about 1 to 5 megawatt electric transportable reactors that a lot of the companies are working on, but they haven't commercialized yet. They're called micro reactors. Factory built, transportable, and you plug and play on site relatively easily, and that's a micro reactor. So when we started looking at Aalo technology and what the market was looking for, micros are too small and their costs are not great because the economies of scale is really against you at that level. So it actually works for remote diesel applications, like remote communities or remote mines where they pay a significant amount of money for energy it works there. But if you think about, in town or powering data centers, the cost does not, work out very well. So you've got the large scale SMRs on one end, you've got micros on the other. What we see ourselves is somewhere in between. And we think it's a new category of reactors where, we have a power output similar to a small modular reactor, but it has the same factory manufacturing capability of a microreactor. So we call this XMR, Extra Modular Reactor, meaning not only just is the reactor modular, but the entire plant is modular, meaning we build all of these as modules in a factory setting and then send them out to the site where they get installed very rapidly. So we don't have to do, very long periods of civil construction project. Only a small fraction of it is done on site.
Yeah.
Next, I want to talk about our products. Now, we've talked about the Aalo Pod, which is our product. That's what the customer buys from us. But the way we think about in Aalo, we actually are working on two products. One is the Aalo Pod that provides power on site, but the other one is the factory that builds these Aalo Pods in a factory setting.
And so we are in the factory setting right now.
And yes, we are sitting in our first factory as we speak. And, essentially, this is not a full-scale factory. This is what we call a pilot factory. I think if you think about these reactors, if we focus on both fabrication and assembly, we can build 16 of these a year in this facility. Now, if we just solely focus on assembly and outsource a lot of the fabrication work elsewhere, then we can, bump that up to about 36 a year.
Okay.
And if you look at it, this is the first nuclear reactor factory in the world. There hasn't been another facility that can make so many reactors annually for a commercial endeavor. So we're really proud of our team. We pulled this whole enterprise here in this facility in less than 6 months. 6 months ago, we moved here. It was an empty shell, and we looked at our reactor design, and we said, okay, we're not developing just one product, we're developing two. So we custom designed the factory to make sure that it's optimized to build a reactor, not just once, but over and over again in a very rapid manner. So it's not fully automated. We use a combination of human skill sets and some automation to come up with this factory operation system. So our goal is to build multiple gigafactories all throughout the United States and make sure that we can keep manufacturing within the United States in the near term and in the long term. Because if you look at previous nuclear technology, if other countries wanted US technology, we would go and build nuclear reactors in their country. So you're essentially handing off the technology to them. But for us, we will make all of those reactors in the United States, and we can actually export them to other allied countries who needs nuclear technologies from the United States. So I think that's a better export model than some of the conventional power plants too.
Well, you're speaking my language. I love it. We want to manufacture in the U.S. We love manufacturing here in Texas. I love manufacturing stuff that we can actually export and sell to the rest of the world, but retain our technology.
That's right.
We cannot continue to transfer our technology and look elsewhere in that manufacturing. So I appreciate what you guys have done. We've talked about this factory, we've toured it, and the thought that went into it, and the process, and the flow, right? We talk about, we had a podcast recently on the theory of constraints, and we talk about flow. You've clearly put that into the design of this factory to test it. I know that there's been a few obstacles, although it looks like the roof is really high. I think you ran into an issue there, and one of our other members helped you through that and redesigned something to deal with that. So it's great, again, to see the ARMA community coming together and how you've reached into that ARMA community. So I thank you again for that and for being an ARMA member and really leading on this nuclear clean energy front. So we're excited. to have that in the portfolio and to see your success and to be here and to support you guys. I appreciate you taking some time. Again, it's a little bit quiet right now. It was a lot noisier when we first got here, but on a rainy day where we've got the doors opened up, we've had an opportunity to really come in and see this. And I hope that you'll check out the website. Where can we find you? Where can the listeners find you guys?
Yeah, it's pretty straightforward. It's www.aalo.com. So aalo.com.
Aalo2as.com. You can really dive into the Aalo Pod technology, the XMR technology that's sitting behind us here right now. Again, some other things just before we go, right? That whole idea is that this can be loaded on the back of a truck, and then you drive it down the road and set it up on the site. And to your point, you can take it wherever you need to. You have regional manufacturing centers in the future. It's really, truly exciting, this technology that we're talking about today. So, again, congratulations to the team for the success that you guys have had so far and continued success. And we look forward to seeing this before the end of the decade out there producing some energy. So, Yaser, thank you so much for spending some time on the Manufacturing Austin podcast today.
Thank you for having me. Appreciate it.